In this video, I'd like to cover integrals. This is one of two videos. And for this video, I'd first like to cover or do a review of what an integral is. We'll define it in terms of an antiderivative, and we'll discuss it in terms of an interpretation being the area under a curve. Then I'll go briefly over some integrals of some simple forms, finally covering cases in which the integral is not in a simple form. We can use some methods to bring it into a simple form, the first of which we'll cover in this video being U substitution. After viewing this video and having practiced with the relevant problems, you will have a review of what an integral is, have a better understanding of that, and be more comfortable at computing integrals of various forms. Okay, so integrals. What is an integral? So let's consider the equation df, capital F, dx, the derivative of f with the capital letters is equal to f in lowercase. So with this equation, big F, the function big F, is considered to be the antiderivative of the function on the right-hand side. So, or more generally, we can describe the equation as the derivative of capital F plus a constant with respect to x equaling lowercase f, in which case the sum of capital F with c can be described as the general antiderivative. It's the general solution to this equation. And this general solution represents an infinite set of solutions, right? One for each value of c. Okay, so that's the general solution. And just to remind you again of some terminology, a solution for a given value of c is a particular solution. So I would say different values of c give different particular solutions. Okay, so we have a general solution and then a particular solution. So the anti-differentiation operation is called integration. The process of taking an antiderivative is integration. And integration is written generally, the general solution is equal to the integral of f of x dx plus our integration constant. So this integral sign looks like a giant S, looks like a large S for sum. As you may recall, integration is an infinite sum. And this notation was introduced by Leibniz as calculus was being developed. And C again is our integration constant. And again, that gives all possible antiderivatives. Okay, so a simple interpretation of an integral is an area under a curve. We can relate an integral to a concept that we might be able to sort of grasp graphically, which is what I meant by interpretation, as an area under the curve. And in this example, I'm going to describe a definite integral, that is integration over dx over a definite interval between a and b. And we can write that in terms of a discrete sum in the limit that a small change in x, or a small increment of x, delta x, goes to 0. So we're going to sum from k equals 1 to n of f evaluated at point x k star, I'll talk about what that is soon, times delta x sub k. So here, let's sketch an arbitrary curve. So here's our curve, whatever it may be, look like. And we'll define our point x0 being equal to a, and then our endpoint xn equaling b in our definite integral. And we can divide this curve, we can divide the curve into discrete sort of rectangles, each having a width of delta x. Or we can approximate the curve as being a number of discrete rectangles. As such, and let's refer to this point as x sub k, this point as x sub k plus 1, and then there's a point between xk and x sub k sub 1. It may be in the middle, or but it need not be, where if we multiply the height evaluated at that point, we can get the area underneath the curve between xk and xk plus 1. And this would be xk minus 1. Okay, and this is the y-axis here is f of x. Okay, so each element of this area is the width, delta x, times this height evaluated at this special value xk star. So f at that value times the width gives a small increment of area, and this equation describes the sum of each of these rectangles, but taking in the limit that delta x goes to 0, right? So as delta x becomes infinitesimal, and by infinitesimal I mean it's non-zero, but smaller than any other number. That's a description, for example, of x approaching 0. So as you can imagine, as doing a sort of thought experiment, as x becomes smaller and smaller, the number of rectangles becomes more and more, and the better it follows this curve. And as delta x becomes infinitesimal, then delta x can be described or written as dx, and the sum becomes an integral. That is, the sum becomes an integral. Or we can replace the sum with the integral sign. So let's talk about how to compute integrals. And part 0 of this is evaluating integrals that have a simple form, simple enough that you can figure it out if you know how to take derivatives. They can be figured out from knowledge of basic derivatives. And so some examples of that are, for example, the integral of a x raised to the n power is equal to a times x to the n plus 1 over n plus 1 plus c. Right? So if we know how to take the derivative of x to the n plus 1, we therefore know how to do the opposite by taking the integral of a to the x. And you can always check your integrals by taking the derivatives of your solutions. And remember I'm adding our integration constant. So for example, if a is equal to x to the 5th power, then the integral is a times x to the 5th power, then the solution is a x to the 6th over 6 plus c. Another relatively simple integral is cosine x dx, and that's equal to the sine of x plus c. We could also take the integral of sine of x being equal to minus cosine of x. Another simple example is e to the a x dx, and that's equal to 1 over a e to the ax plus c. And then the integral of 1 over x dx is equal to the log of x plus c. What about, and I'm going to pose this question to you and have you work it out on your own real quick, but what about the integral of hyperbolic cosine of x? And to give you a hint on how to evaluate that, I'll remind you that cosh x is equal to e to the x plus e to the minus x over 2. So you should be able to figure that out. I said I was going to cover U substitution, but I'd like to keep the videos close to 20 minutes. So I'm going to end this video here. So we've covered our definition, and we looked at some integrals of some simple forms. You know, the integrals of simple forms can be sort of displayed on a single page in a calculus textbook. So I encourage you to go back and look at your calculus textbook, or even look online for these simple integrals, just to remind you of these forms, which you should, well, you should be able to remember many of them as you apply those in this class. So I'll end here with this video and continue on the next one.